Yes, thank you very much for the nice introduction. So, yeah, as already introduced the topic, I will switch to the next slide. This is my team, so because yeah, we are facing a very complex topic, and this can only be achieved by an interdisciplinary group, which we are based on, or which consists of engineers, material scientists, physicists, and mathematicians. And therefore, we cover, in addition to fracture mechanics, a wide range of different topics. So, including robotics, software development, and of course, machine learning. So, what's our motivation today? So, if we think about bringing a new aircraft into service, we need to perform a lot of tests to ensure a safe operation when it's in service, and therefore we need to perform a lot of physical tests. So starting at fatigue crack growth tests at component level. So with a specimen with the size of a sheet of paper, and end with full-scale tests by testing a whole aircraft. And of course, this requires a lot of time and money, and yeah, it takes very long. So therefore, our motivation is to reduce the number of tests by more focused testing to learn the physical behavior of, in this example, fatigue crack growth, and merge the results into a physics-based model for which we can use in simulations for, in the case of virtual certification and qualification. Therefore, our biaxial testing machine is a perfect tool to do this, because we can subject specimen of relevant size with relevant loading conditions, biaxial loading conditions, which we have in the fuselage section of the aircraft. And what we are looking for are effects like the influence of the load ratio, crack closure mechanisms, the influence of the plastic zone, crack branching, crack deflection, and this is all based on the microscopic level. And to tackle this challenge, we need data. We need a lot of data. And therefore, we enhanced our biaxial testing machine that you can see here by automated methods and by digital methods. So therefore, we had a lot of requirements. For example, we wanted to measure the deformation field of the specimen during test. We wanted high resolution data, so in the millimeter range. We wanted a high spatial and temporal resolution of the data. And because of the large amount of data, we wanted automated methods for the evaluation. And this resulted in a completely automated testing machine that we can see here, that combines digital image correlation with robotics and an optical microscope that you can see here. Above the specimen, there is a 3D DLC system which observes the whole testing area. And finally, so for evaluation of the data, we developed our own toolkit called CrackBite. It's a Paysan-based toolkit that is open source available and that everybody here can use. So this is our test setup, and now we go to the test sequence. The test sequence is divided into a crack propagation phase and an image acquisition phase. So if we consider for this specimen a straight crack, then the force on the y-axis controls our K1, while the force on the x-axis is directly proportional to the T-stress of this straight crack. Yeah, then we load the specimen in this example with a constant amplitude and in phase loading, and yeah, observe the propagating crack. At specific crack growth intervals, we stop the machine and take an image with the 3D system, which observes the whole testing area. And we get images like this. The spatial resolution is yeah, quite low, with about 2 mm per facet, but we can perfectly see the crack paths here in red. After that, we detect the crack tip position for the left and right crack tip, and the robot moves the microscope to the actually present crack tip position. And here we have a much higher resolution, and we can see localized effects, so like crack kinking, or here the plastic zone in red. And yeah, we get a lot of beautiful data of during the whole test. And after this sequence, the whole procedure is continued again. So in a closed loop, then we do crack propagation again, and yeah, take images until the specimen is completely broken. In this example, we investigated the aluminum alloy 2024 T3, and first the crack to kink, because we incrementally increased the T-stress. So we wanted to know why, yeah, the crack is, or how the crack deflects. A method that enables all this is the crack detection during the experiment. So the crack tip position, and especially the crack orientation, is the most important information in fracture mechanics to evaluate, or for quantitative evaluation of DAC data. And therefore, we have two redundant methods. So one method is the so-called line intercept method, combined with a crack tip correction module. And here we look for displacement gradients in the y direction, and they determine after that the crack tip position. More details on this method will be given later by Dr. Melching, so please stay tuned. On the other hand, we have trained a machine learning model that we call parallel nets, and this model is a combination of a unit-based architecture for image segmentation combined with a fully connected neural network during training by a common loss function. And this has significantly improved the robustness of this network, because we can segment crack tips even for unseen data, for new data sets. Yeah, and this is also open source available in Breitbarth, so you can try it out yourself for your data, for your own data. And after we know the crack tip position, we can do a quantitative evaluation, as we have seen in the talk before. So we can determine the stress intensity factors, the J integral, the T stress, and higher order terms of the so-called Williams series expansion. And therefore, two different methods are implemented. The over-deterministic method, which fits a theoretical field of the around the crack tip to the actually present displacement data. And here we use the Williams series expansion and the Christopher James Patterson model. And on the other hand, we have implemented a line integration method for the J integral, interaction integral, and Bücker J integral. So we have also here a lot of redundant information, and this can be used yeah, for uncertainty evaluation, and yeah, to judge about the quality of the data we collected during the experiment. Now we see the whole system in action. Yeah, the movie is working. So in this video, we see the whole system, or how the whole system is operating. So first, we take an image of the whole testing area. We detect the crack tip on the right-hand side. on the left-hand side, and then we move the microscope exactly to these positions to take high-resolution images of the corrected area. Not only a single image, but rather a set of images in a checkerboard pattern like this. And here we can see the beautiful crack path, the black-white pattern from DIC analysis. And of course, we can stitch together the images. And now we see the DIC evaluation and the plastic zone and the cracker. So which with a much higher resolution. And then the whole process is repeated on the for the other side of the crack. We do it at minimum and maximum loading, or we take images during a load cycle. So and all this can be predefined before testing. And the big advantage is that this system can operate 24/7 without human interaction. So the complete test sequence is automated. Yeah, and here again, so now the next sequence starts. Here is an animation, how we recognize the crack tip of the growing crack when the crack kinks, because we increase the T-stress in steps, so until the crack kinked. Then we forced it by a pure mode 1 loading to grow again straight, and after that we forced the crack again by increasing the T-stress to kink. Each single image we see here is an individual image we took during the test, and after the test we have 300 to 400 gigabytes of data, so which is very much, so which is a very large data set. And then another example how we trace the crack with the microscopic data, and even here the crack tip detection operates very well, and we can see local differences in the crack path. Of course, here we need to divide from real data and scattering data, so which we do afterwards. But we get a lot of data during the experiment. A big topic is the visualization of the data, because only a good visualization can make it usable for other people. So only such a web interface we developed here, where you can play around with the data, makes the data findable, accessible, interoperable, and reusable, so for other people, according to the FAIR principle. And we also publish data and share data with others. This is our intention for the experiments. In this example is an animation showing how we evaluate each single data set, and we get a feature vector like this for every single DIC image. And all the data I mentioned before for the evaluation of the jet integral and the stress intensity factors are listed here. And this allows us to do data science. So this enables us to apply data science methods to look for unseen correlations in these kind of data sets. Sorry. Now I come to the conclusion. So we have seen that robotics is a great tool in experimental mechanics, because we always know the exact position where an image was taken. So in kind of metadata, it makes or automated without human interaction. Because of the different evaluation methods and redundant data, we have this creates confidence and trust in the data. The FAIR principles are applied here. A little disadvantage is that all this requires coding skills, so you must know how to program the test sequence. But we are working on this to make it much more easier. And so from my point of view, there's a need in the community, in the fraction mechanics community, for standardized data formats so that we can change or exchange data. So even in between different teams and groups, because this is an enabler for accelerating knowledge discovery, so that we don't need to repeat each experiment again. So yeah, that's my presentation. Thank you very much.